I'm really humbled and honored to be the Dean of the Granger College of Engineering, and I'm really excited today to moderate this panel. So I'm going to also have a seat here, and we'll try to get started. So first of all, again, thank you all for being here. I want to thank our panelists for being here. Again, on behalf of P33, Intersect Illinois, and the Council of Global Affairs, really welcome to Chicago, and welcome to the Global Quantum Forum. I'm also on the board of P33, so just a pitch in for them. I think they've done great work, again, collaboratively across the entire ecosystem here to build, kind of where we are at. So we have, I think, a very interesting and exciting topic, and it's something that actually the answer might not be very clear, right? We want panels and we want discussions to help us kind of chart the way and be able to think about what is true, what is not, what is hype, what's reality. We also want to really kind of keep a focus on that. So when you think about quantum and you think about data centers, there is a question of how the two might intersect and work together or not. So over the last decade, as data centers have integrated hybrid computing across CPUs, GPUs, and TPUs to tackle some of society's biggest computing problems and to really expand and activate this AI ML revolution. Illinois is also home to multiple data centers, and certainly more recently, with the governor's support and working with the state, there's been multiple new data centers that have also been set up here. And in parallel, as you know already, as quantum hardware development progresses, and we approach the goal of realizing the first fault-tolerant quantum computer here in Chicago, we'd like to discuss these opportunities and challenges of how the quantum computers might integrate our interface with data centers. So that's really kind of the goal today. We have a fantastic panel. I'll just call out their names really quickly first. So hold your applause till after. And then I'll go through a set of questions. So we have Michael Brett with us from Amazon Web Services. We have Alex Etkin with us from Optiver. We have Kristen Wasmeyer here from JLL Work Dynamics. We have Kanav Satya from QBraid. And last but certainly not the least, we have Andrew Jurek, who came from the furthest away, from Australia. He's from Dirac. So thank you all. Let's give them a round of applause just for being there. Okay, so I'll put a first question forward, and then I'll ask maybe everyone to say a few things that they want about what you're doing in your company, very briefly, but also then kind of try to answer this question. So how will quantum computers, or QPUs, quantum processing units, be integrated or work together with data centers? And is data center integration really necessary to make quantum computers useful? That's kind of at a broad sense, at a high level. So we'll start there, and then we'll dig deeper into it. So I'll lead off with Andrew.
Yeah, thanks very much, Rashid. So I'm Andrew Jurek. I'm the CEO and founder of Dirac. We're a quantum computing company that's developing quantum computers based on the same silicon technology we use in all our phones and laptops today, which means we can put millions of these on a single chip and make very, very compact and affordable quantum computers. So coming to your question, Rashid, there is going to be a very, very close relationship between data centers as they are today and quantum computers in the future. And the reason for that comes to the fact that most of the important commercially valuable problems are going to require a huge amount of classical compute alongside quantum computing. When the poll was taken, I think in the second panel, we saw healthcare at the top. And that's because one of the bigger applications of quantum computing is to quickly find new drugs that can be trialed to reduce the costs of clinical trials. I mean, this could save billions of dollars for the pharmaceutical industry. But in order to do that, you don't just go to a quantum computer and say, find me a drug. You actually need a large amount of AI to initially find potential candidate molecules, and then you need to feed those to a quantum computer and either calculate it serially or preferably have a whole bunch of quantum computers in parallel. So ultimately, I've given just one example there, but pretty much all of the commercially valuable problems require a large amount of classical compute. And so that means you need to be certainly closely related to data centers. I think we're going to come to the question of whether you need to physically co-locate In our view, we think that there will be great benefits, but we'll perhaps come to that later.
Okay, thank you. Thank you. Kanav, what do you think? You want to add to that?
Kanav Sethi, I'm a co-founder and CEO of QBraid. We are a one-stop platform for getting access to quantum software and quantum hardware. Our user base is over 21,000 and consists of users from over 400 universities. So if you're ever thinking of getting easier access to quantum software, quantum hardware, go to QBraid. Coming back to the question of data center co-location, I think that the way I like to think about it is if large amounts of compute is a commodity, then data center is a finished product. So ultimately, I think it is going to happen where you're going to have quantum computers co-located in data center, but in what quantity and how they would be done, it will partly be related to a lot of the market forces. So for example, if you go back like 10 years, most of the data centers consisted of high amounts of CPUs and not lots of GPUs. So now there are data centers primarily consisting of GPUs, and then there's a whole bunch which are CPUs plus GPUs. And that's how I think QPUs are going to evolve as well, where, as Andrew mentioned, there are a lot of quantum QPU modalities that require lots of classical compute and with low latency. So that means the only way you can achieve that is put QPUs in a data center. But there are a few other modalities which may not require. And so which one ultimately wins and what are market forces driving how much usage will describe how many quantum computers are in data centers.
Okay, all right. Kristen, your view on this? And introduction also.
So JLL is a global real estate services provider, from markets advisory and brokerage, capital markets, finance, investments, through property management and facility management, and all the services from energy procurement through sustainability and technology. My job is not to tell you if we're going to integrate the QPUs and the GPUs. My job as a real estate advisor is to say, this is what's going to happen if we go down this path or that path, from property acquisition perspective, from a financing perspective, and most importantly, I think, as an operator at heart, what does that mean from a facilities management perspective? What kind of externalities can you expect? And as your business or your university evolves, how can we as a service provider lend credibility to your business plan for that? So I think regardless of the way the integration goes, we look at ourselves as how can we facilitate our customers to succeed?
Okay, thank you. And that's very, very important. Thank you so much. Alex?
Hi, my name is Alex Itkin. I'm the US CTO at Optiver. Optiver is a global electronic market-making firm, so coming at this problem from an even different perspective, kind of a third view on it. We operate data centers, we operate in the cloud, we do a little bit of everything. I would say as a potential consumer of quantum computing or quantum technology more broadly, I would say we would be considering all the options, ranging from deploying quantum technology directly in a data center where we are managing all the space, but then we're already also using, whether it's infrastructure as a service, platform as a service, or pure software as a service models, right? So if you're doing things in the cloud, if you're buying software directly from a vendor, and it's really just a trade-off of what are you looking for, right? So I think with quantum computing, it'll be quite similar. Is it a balance of cost, time to market, your ability to get access to certain technologies, right? So deploying in our own data center might not be feasible, given how quickly some things change. So I think we would be considering it much more from the perspective of what are the trade-offs that we're trying to balance here. So we would be certainly open to any of those possible models. And it's just a matter of what that execution looks like.
Okay, thank you. Michael?
Hi, everybody. My name is Michael Brett. I lead business development for Quantum at Amazon Web Services. And as a global cloud services provider, we operate data centers. That is our core business. And integrating quantum computers into that business is absolutely part of our mission. For the last 5 years or so, we've been running a service on AWS called Bracket. And Bracket is where we make available quantum computers to our customers today. So all of you in the room today, this afternoon, you can get access to quantum computers through AWS. But those computers are not currently sitting in our data centers. Those computers are with the manufacturer of those quantum computers. So today we've got 8 different computers from 4 different providers, wonderful partnerships with IonQ, Rigetti, IQM in Europe, and QEra. But they operate those computers. They built and operate them, and then we connect into them from the data center today. And that's how we've been operating for the last 5 years or so. Over the next decade, we anticipate that we'll start bringing that into our data centers and start doing that integration work of hybrid classical quantum compute to deliver the kind of applications that the others have talked about. And that challenge that we're on right now is a big effort that we're going to have to go through together in partnership with everybody here.
Okay, great, thank you. So let's dig a little bit deeper into this question again. And I would say, so maybe we can talk about like what specific benefits could the QPU data center integration really bring to the various stakeholders, and especially for specific applications perhaps, and specific algorithm developments. What kind of problems need the co-location of data centers? Are there latency considerations, obviously? So maybe we can go into that a little bit. I'll ask Kanav, maybe you can start us off and try to answer a little bit more specifically. Yes.
Absolutely. So the first thing, what Michael mentioned, I think the way people think about quantum computing development is many times they argue, hey, you have semiconductor pipeline, the technology developed, you want to leverage it to develop new quantum chips. And the same analogy carries over in data center as well, where now you have, if quantum computers developed, you want to be leveraging all the data center improvement and improvement we've had over the decades, understanding and leverage that in productizing that new compute. So all the things you can imagine in physical space, like the security aspects, how to design data center, how to design power supplies and so on, they come into play. So all those advantages, makes sense that you just put your quantum computers in data centers and you'll have all of that architecture powering that. From the algorithm point of view, there are 2 main aspects. One is the requirement of classical compute by quantum computers themselves. Today's quantum computers are quite noisy, and you need to use something called quantum error correction, where what you do is you build redundancy in quantum computer, run the calculation, do a lot of measurements, and then you do a lot of post-processing to figure out where the error happens, and that post-processing happens on CPUs and GPUs. So quantum computers themselves need a lot of classical computer at very low latency. So that puts an immediate requirement that you need to put quantum computers right next to lots of compute. Data centers are the best place to do that. And then the next model that Andrew already touched upon, most of the community believes that ultimately it's not going to be quantum computer magic key and does everything. It's going to be algorithms which are hybrid, where part of the calculation runs on CPUs, GPUs, and then QPUs. And again, if you want to do all of that, it would be cool to have all of them in one place. Plus, in general, you would have low latency, low overhead of network requirements. So I think the ultimately productized version of quantum compute is in data centers.
Anyone would like to add anything? Alex, do you want to say anything on that, to that?
Yeah, I think you raised some really good points. And I guess for some perspective, so, Optiver, we're already running dozens of different data centers across the world, multiple in the US, multiple in Illinois here. And to your point of if you're trying to pair classical compute, whether it's CPU and GPU with quantum compute, we already have data centers filled with CPUs and GPUs, and even the evolution from going from primarily CPU workloads to GPU workloads, as much as people out there are talking about buying lots and lots of GPUs. In most cases, these large data centers also have lots and lots of CPUs because there's certain things that you still want to do on a CPU versus a GPU. And if you kind of extend that analogy to quantum computing, I think the same thing makes sense, right? So if we're already doing our research in a location somewhere in the US where we have lots of GPUs paired with lots of CPUs, and what we don't even mention here is kind of the data locality part of it. So we have lots and lots of proprietary data that we're storing also on very bespoke, high-performance devices. Being able to co-locate whatever that next compute modality next to it is certainly quite appealing. And then the other thing you touched on there, which I think is very interesting, is the whole ecosystem of the data center, the network connectivity. You kind of hinted at that, but that's actually quite large when you're running a distributed setup across many different locations. What is your ability to actually get information and data from one place to another? Certainly, if you're talking about the finance industry, the idea of co-location relative to the external venues where you're going to be interacting with, the primary one being exchanges. That's a big driver of where you deploy your compute. And then the question of latency and what kind of calculations and what kind of algorithms do you actually have to run close to the hot loop versus you can offload the calculations more offline or maybe use it more for some of the research rather than your production, your execution setup, I think would all play a factor in that.
Okay.
So just to give you a really concrete sense of the scale that's required here and some of the resources that we need, we recently published some work that we did in partnership with IonQ, NVIDIA, and AstraZeneca, looking at a particular molecule that AstraZeneca was interested in. And modeling that molecule took about 3 days of processing time on one IonQ computer, followed by 5 days of processing time on about 120 H100 NVIDIA GPUs. A huge amount of capacity from AWS went into supporting that one workload, which completed in 5 days, and then we redistribute that compute back out to other customers for what they need to do. So once we start to think about how we scale that up to hundreds of customers in global locations with data residency requirements, and add networking and controls and security and all the orchestration tools around that, the effort required to connect a global quantum computing platform that serves every customer in the way that they want with the classical compute that sits alongside that is a really, really big deal. And that's why we're investing quite a lot of time in figuring out how we do that integration piece along the way.
Okay. So let me just follow up on that. I'm going to go off script, of course. But, so what about this the latency consideration? Is it a function of the kind of problems you're going to be working on or the end customer is working on? Do you really need the co-location if the latency considerations are not that critical on the kind of problems you're solving? And also, we're talking about the computers today versus getting to a fault-tolerant quantum computer. So is there a different situation in the two cases where the computers are small, the quantum computers are smaller now versus getting to the, let's say, the fault-tolerant situation?
So just quickly, the answer is yes, both. And there are some cases where we have very high latency sensitivity, and we need to have co-location to be able to support particular algorithms. In other cases, not so latency sensitive. And so we can kind of relax a little bit more and go, well, maybe we can get the capacity in a different region or a different price or a different allocation time for those particular QPUs, which really changes the pricing dynamics and the demand dynamics around that and where we co-locate things. So that is a big sort of dynamic question where, yes, we're going to need co-location and very close quantum classical compute. Other times, not so much, and that's something that we'll sort of play with over time.
Andrew, you have
Just to
yes, please.
jump in there, I
Please.
think one of the interesting things from a real estate perspective that lends to that is we're kind of at a point now where in terms of real estate development, we're hyper-focused on those CPU, GPUs, server farms. We are hiring hundreds of people in West Texas that had no idea a year ago they were going to work in a data center. As that's part of the compute equation gets solved, the market will naturally shift back into more of an inferencing edge type of real estate development plan. And what's great about the timing of not just this conference, but the advent of QPU is now we can start taking that into the calculation from a site selection, from a supply chain perspective, design, build, commissioning philosophies. We'll be able to integrate that as the market moves.
So actually did you have anything to add on that?
Oh, I was just going to come back to the point, I think, on latency.
Yes.
And Ganav mentioned it before that quantum computers, particularly when they reach full scale error-corrected systems, which are really the very, very commercially valuable systems, require a lot of classical processing for the quantum error correction. And so that's where actually having co-location can be valuable just to make the quantum computing possible. Now, the hybrid algorithm aspect, because most quantum algorithms on the quantum processor are going to run on timescales of, let's say, hours, sometimes days, their latency is not so important. So I think it's going to be more the co-integration supporting the quantum computer. However, I think there's another aspect, not so much about latency, but more about data security where, and I think it's already been touched on by Michael and others, where having co-location will be important. Because quantum computers, as we heard, I think 2 panels ago, on the geopolitical aspects, there are incredible national security aspects of quantum computers, and there having everything located in one space could be very, very important.
Excellent. So let me follow up on some of the requirements of co-locating it, for example. I mean, what can you comment on main technical operational hurdles? So for example, we know quantum computers will need extreme cooling. You got to get temperatures down to apps close to 0, or electromagnetic shielding. So from that perspective, are there, data centers need a lot of energy. Quantum computers will not need as much energy. So are there any sort of pros and cons from that perspective, or any considerations of energy, thermal management, electromagnetic shielding, temperature requirements when you co-locate?
If you forgive me to go again.
Please, yes.
So it depends on the actual implementation of the quantum computing, because as people may be aware, there's a number of different paradigms being studied at the moment, and each of them have different requirements in terms of size and energy requirements. So I think everyone's here, very excited about what's going on in Illinois with PsiQuantum, amazing company, great scientists and engineers, and the vision they've got to build their quantum computing system here is very exciting. I was actually down at the South Chicago site to see where that quantum computer is going to be built. In the case of Psi, it's looking at a football field size system, obviously with significant power requirements. We heard from our sponsor and host of the sorts of energy that can be required for a system like that. So in that case, it may be more of a case where the quantum computer sits alongside a data center. Our particular technology, conflict of interest, I have to say, our whole focus is on making very compact systems. We're looking at just 20 square feet to make a error-corrected quantum computer, and very, very low energy consumption. And so in our case, we're actually looking at putting our quantum computers inside data centers. In fact, having potentially hundreds of quantum computers that can operate running parallel problems being fed by that advanced AI. So I think it's a bit horses for courses. It's going to depend on ultimately what technologies ultimately prove to be the most effective.
Okay. And in that case, in your situation, for example, the approach you are taking, is that going to be suitable for any particular type of applications, the end applications versus not?
When you have an error-corrected quantum computer, in general, it'll be able to cover a whole range of applications, and it'll go for all those technologies. So it's not so much that particular quantum computers at full scale will be better for one than another. But just one other point about the issue of some of the challenges. Pretty much all quantum computing systems, no matter what technology, require cryogenic cooling of some form, because quantum states are very fragile, and temperature damages the fragile qubit states. So generally, they all need cryogenics, including our own. So for our system, for the Psi systems, for all of them, superconducting systems that we talked about before, you're going to need cryogenic infrastructure built in with the data center.
Yeah. And that's exactly why, as all of you heard earlier too, we're building, the world's largest cryo facility here in Chicago, in South Chicago. Please.
Just to add to that as well, for AWS, one of the big challenges we need to address is the people side of how do we install and support and maintain quantum computers in our data centers. These are incredibly secure facilities. I've worked for AWS for 5 years. I've never even seen one of our data centers, let alone gone inside one. And then that's for the public cloud. We also have government customers that we operate data centers on their behalf that are secret and top secret, air-gapped regions with have very stringent security requirements. So our ability to bring a computer inside the data center, install it, integrate it, provide all the equipment, and then maybe maintain it or support it or do upgrades, having the people infrastructure to be able to do that as well, that's going to be a really big deal, not only in the US, but all over the world to serve global customers. So, as we think about scaling that out, it's going to be a problem for us to solve.
Well, let me take you up further on that, or just, I guess, everyone, but I think this issue of security, let's talk about that for a little bit. So, what impact will this integration have? So if you're putting, I mean, currently quantum technology clearly is a matter of national security and a national priority. It's going to be a global race on this, and it already is. I mean, a quantum computing facility where you can get to a fault-tolerant quantum computer, you think the security concerns are the same or different than a data center security? I'm talking about physical security, cybersecurity. So is there any sort of considerations you have to make when you talk about that? I agree that you, like you said, you run data centers, you manage data centers, but you probably haven't been to one. But when you have a quantum computer, a fault-tolerant quantum computer, the security considerations are going to be the same or different?
I can maybe start with the physical
yes,
security.
Please.
I have no right to speak on cybersecurity, as can't even figure out my kid's iPhone password. But from a physical security perspective, the hyperscale data center, the GPU data center industry is already designed around kind of what you pointed out, 7 layers of security. I think the complexities of the QPU add a different operating environment, and we might touch on that a little bit later too. But that operating environment is going to require, one, a different playbook from a security perspective. It's also going to create a different level for the security personnel working that. You know, at this moment, you can walk a mechanical aisle, an electrical aisle in your Skechers within a data center. Well, now if you're going around QPUs, they're very sensitive to vibration, they're very sensitive to EM. So you're gonna have to train them on the why behind this so that they really understand with the proper amount of vigilance how to take care of a data center that has QPUs from a security perspective. That extends to supply chain management and logistics as well. There's a much more robust chain of command requirement for QPU infrastructure than there is for GPU, CPU. And so that just requires a retooling of the playbook and investment in that layer of the physical security.
Okay.
I can go.
Yes, please.
I think one of the things, so there's cybersecurity that could be broken by quantum protocols and quantum algorithms, and that's attracted a lot of attention. People have talked about how using quantum computers you can break Bitcoin and all of that. That's been discussed a decent amount. What I think is lacking is discussion around security protocols around quantum computers. So right now, people have been hyper-focused on making quantum computers work, and there's very minimal research around, is there a way to, if somebody's running a calculation, maybe later on learn about what they ran, right? The security aspects within quantum computing is lacking, and this is where I think another place we would love to invite the community to come in and focus on doing some more research. We've got few customer university professors doing research, trying to understand what the cybersecurity in quantum realm would look like. But as I mentioned, it's very minimal and requires a lot more attention.
Okay.
Right.
Yes, please.
I just wanted to add that the sorts of problems that are going to be very commercially valuable, I mean, I talked about pharma, but there's problems in financial modeling and so on. It turns out that when quantum computers reach the scale of millions of qubits that are required to really crack those problems in a meaningful commercial way, they will already be at the stage where they can crack public key encryption, RSA 129. So these are all in the same area. So what that means is that all of a sudden, utility scale quantum computers, commercially valuable quantum computers, the types that we want in data centers, actually need to be in a secure environment. And as Michael was saying, some of the most secure environments we have are high security data centers. So I think that's another reason why ultimately these two go together very well and will naturally be in one location under the same security regime. It will also mean that the location of these data centers will have to be very carefully controlled. I think ultimately, we heard about the geopolitics. There'll be certain countries where it'll be okay to have them located and other countries not so much.
Yeah, I was actually going to ask that next is, when it comes to data center, the sovereign cloud capabilities have been talked about as a consideration. So what does that mean for QPUs and data centers? I think you just answered that question, but
yeah, absolutely. I think that quantum enhanced data centers will be core sovereign capabilities for nations that have close security ties. Obviously, NATO countries, US, Australia, UK, Western Europe, but I can see, and obviously, friendly democracies in Asia, such as Japan and South Korea. But there's going to be definitely a grey zone in between as to which countries can share that sort of data capability.
Good. Okay. I want to kind of give one more opportunity to address this question a little bit deeper if needed, maybe Kristen yourself, about this from a developer's perspective. So, what are the challenges of integration of data centers and quantum computers? You talked a little bit about it, but is there something that from a developer community, are you all thinking about it? Are you preparing?
We have it all figured out.
Workforce, you've got the playbook ready to go.
Look, I think the things that a quantum data center and a traditional data center have in common, they're very capital intensive. So new developers coming into the space, it's not for the faint of heart. If you're going from commercial to data centers, there's a lot of sticker shock element to that. You won't have that going into quantum, although if you just judge it on a cost per megawatt basis, that's probably not the right calculation to avoid heart palpitations. The things from a site selection perspective, power, stability of power with a good grid provider, we talked about ComEd at the beginning, that's a key congruent factor between QPUs and GPUs. From there, you get to a little bit of a conundrum for QPU data centers. We like no vibration, we like low EM. So that would suggest to you that in rural areas, you're going to find better plots of land that are suited to develop that and have a better ecosystem for you. But the current state of the QPU industry, we need to be in the major metropolitan areas that have research hubs, scientists. We're going to talk a lot about talent throughout today and tomorrow, I imagine. So that gives you an urban site location development plan. Where Chicago is developed on the south side is very smartly placed, right? It's close. Everybody can get there, but it's still isolated in its own way. So you can control the regional factors. Even as the region develops, you're able to minimize the externalities on what are ultimately very secure and sensitive facilities. I think if you look at the redevelopment of industrial buildings, I think there's a play there. Certainly, you have to do a lot more rigorous due diligence around your civil, mechanical, structural elements of the building. You have to do more due diligence on the environmentals and the EM controls, but I think it's a very viable path. And there's a lot of those buildings throughout major industrial cities that you can flip. From a greenfield perspective, it's kind of an optimism for the future statement. There are a lot of advancements in modular construction for data centers right now that incorporate advanced power requirements, advanced cooling requirements. We talk a lot about liquid to chip, liquid immersion technologies, and we're solving that in many cases in a modular sense that it's easy to expand and extrapolate the form factor to incorporate QPUs into GPUs. I'd be remiss if the operator in me didn't state this, though. From a facility management perspective, it does require a bit of a shift of focus, similar to physical security. Currently, QPUs are in a lab environment, highly controlled. University settings are typically very adept at this. And at lower scales, lower quantities, sub 500 kW, that works just fine. As you start scaling and the facility operations scales, you go from a CPU and a GPU facility, which our core tenets is uptime for those facilities. In QPU terms, it's coherence, or the physics of it, and the non-disruption. We talked about the Bears earlier, so we'll give the Blackhawks a shout out. If you're an ice hockey team and you are in the middle of a game, you can switch on the fly and still keep your strategy and try and win the game. If you're a rowing crew on the middle of the Chicago River and you try and swap out one of your oarsmen, your boat's gonna just go like that, and you're not gonna get to the end destination. And that's what facility management faces in a paradigm for this. Now you combine those two, and now you have an entirely new set of dynamics that you have to work for, and then you get back to the skill sets that you need to train that and develop that and coherently run a facility that has these different kinds of computes and compute needs.
Can I just jump in and say that, I mean, this is something that our company, Dirac, is really actively working on. So we're currently talking to data center providers, both here in the US and in Australia, to get some of our early stage quantum processing units in there to test out exactly the issues you're talking about, to check the robustness against EM interference, to make sure that we can conveniently get the cryogenics in there without any dramas, and ensure that, and also just deal with the security environment that there is.
Great. So let me follow up on the next question of talent. I think this was mentioned earlier in the last panel too, and by IBM as well. So talent is in demand, huge demand. We have a shortage of talent, I think I would say in the US and across the world certainly too. And I mean, we are from a university perspective as well in the business of developing that talent. So what kind of talent pool you think is needed, sort of new talent or new expertise, new just kind of training when you think about this integration? Perhaps it's quantum and AI, but also quantum in this kind of the data center space, right? So what kind of talent would you be looking for from your perspective domains as these two worlds come together in certain applications and certain situations, like it's been mentioned, data centers and QPUs? What kind of talent would be needed? What expertise would be needed? Start off with you.
Sure. One of everything, please.
One of everything.
Yeah,
that's right. An electrical engineer, mechanic, computer science, everyone.
We'll take everything you've got available. But yeah, I think adaptability is the key. Like, this is going to be a very fast-changing industry. We are in a very nascent stage right now with some early-stage computers that can do some interesting things. But as we scale up and we solve some of these problems, and then we deploy quantum computers into data centers globally, the requirements for that talent are going to change very quickly in a short amount of time. So being trained for those tech skills, both at a postgraduate level to help us design quantum computers, but then a technician level, skilled technician level to be able to do installation, support, upgrades, that kind of work, they will need to be a very adaptable workforce over time. And so that remains.
Okay. All right. Any comments on that?
Maybe one thing I would highlight, even in the transition from primarily deploying CPU-based infrastructure to GPU-based infrastructure, you see from an operational perspective and the data center engineering perspective, it's quite different. The failure modes of deploying kind of classic CPUs is very different than when you have a very high power environment of GPUs, very, very tightly packed. Like, you can't stick your hand in there to unplug one of these cables. Like, it's a very, very different environment than what a data center would have looked like, let's say, 10 years ago. So if you're thinking about the kind of person that's going into the data center and what can they actually do, if you're talking about CPUs, they can literally take a machine out of a rack, put a new one in, plug some cables in. It doesn't look so different than what you might have in your basement. If you're talking about GPUs, already you most likely are not doing that. You're taking an entire rack that's very tightly integrated. You're not going to be rewiring these things in person. So if you take that further to what it looks like when you have a quantum computer, whatever format that looks like, obviously we're discussing a few different formats, like that's a whole new world, right? So you're going from potentially taking a kind of a classic looking computer in and out of a rack to taking an entire rack of GPUs tightly integrated with networking and storage to then an entire quantum computer. I think that will require quite a different type of operational skill set. And I will also piggyback off that saying, kind of based on what you were saying earlier, Kristen, building data centers is all over the country is not the same experience. Some places are very good to build data centers. Actually, Illinois and the Chicagoland area is a great place to build data centers. Mm-hmm. Some places it's actually quite difficult because you don't have the density of people that can actually do the work for you. And it's not just the building it once, it's actually the operating it time and time again for years. And I think that ecosystem still has to develop. And you've seen that it's already changed quite a lot in the last 3-4 years with people trying to build these massive AI-centered data centers where you're seeing data centers being developed in new parts of the country where previously maybe that wasn't happening. And then you're figuring out who's actually going to do the work there, who's going to go in there and deploy all this hardware. So I think with quantum, you'll see kind of a further evolution and a further set of challenges there.
Okay, great. Can I riff off that point and just make the point, coming back to Illinois, that I think that, as I was saying before, installing quantum computers co-located with data centers, there are a number of engineering and technical challenges, scientific challenges have to be worked through. And so you really want that talent, as everyone's been saying. And so, again, Illinois is a great place for it. I mean, you've got University of Chicago, UI, UC, amazing talent pool. And I mean, to be honest, that's what drew our company Dirac here to Illinois. We're setting up our first US-based R&D lab here within
great.
the next
Yes.
year. Very excited to be doing that.
Big round of applause for that. Yes.
Thanks. Yeah, no, we're super excited to be here, and a lot of that is about the talent that is based here. And so we were hearing that before. You want to, when you're developing advanced data centers, you want that talent nearby, and that's something that Illinois has got in spades.
Great. And I think we have the same situation with quantum as well. Data centers and quantum. We have, I think, given the regional universities even, and in Chicago, with Northwestern, UIC, UChicago, UIUC, and the region, I think we produce like the most number of engineers in computer science in the country, really, if you look at like a 200-mile radius. So I think that's a great opportunity, and I hope a great attraction for companies to also come here.
Just to broaden that
please,
from a local perspective,
Yes.
we operate a lot of facilities here in the Chicagoland area and have a very strong partnership with the local union 399. And down the road, they have an amazing training facility that journeyed them from healthcare to office space and old boiler systems into data centers, CPUs, GPUs. And the partnership that the union has with the local businesses to get to the latest technology, understand how it works together, that's starting to incubate the next generation of facility staff. And we're already seeing that pay dividends in the GPU side here in the Chicagoland area. And I think that's another area to double down on as you get into the QPU area.
Okay, great.
Yeah, I think one of the things that we didn't address too much is the software aspect of it. The orchestration layer, the thing that makes data center compute dense. Like if you have one of the GPUs failing, there's one aspect you got to replace it, but there's another aspect, okay, rebalance the load on other computers, right? So you've got 100 quantum computers, one of them fails, how do you like dynamically manage the workload on other quantum computers? And that's probably going to require new kind of quantum software engineers, and there's going to be a huge requirement of those engineers in a field actually which honestly doesn't even exist right now. So it's going to be an overlap of like DevOps, orchestration engineers, coupled with a decent amount of quantum computing knowledge.
Okay, great. Well, thank you so much. I think we're going to come close to the end of the panel, so I want to give one more opportunity to each one of you to perhaps one or two punchlines, right, about quantum, QPUs and data centers. Yes, no, under certain conditions. Can I just do a brief summary? I'll start with you, Mike.
Definitely yes.
Definitely
I think
yes,
the
okay.
quantum computers and data centers are going to go together. I mean, our company's looking at having hundreds, if not thousands, of our systems inside single data centers. So we're looking forward to that future. Very exciting.
Okay, so you're a yes. Okay.
Definitely
All
yes.
right.
I think so, yeah, yes for me too. I think ultimately we're going to need a finished product for a large amount of compute, and that's what data center is.
Okay.
It's a yes, but it's an and. They're all going to grow.
Yeah. And maybe under certain conditions, right? Still, I think, but mostly yes. That's what it looks like, at least from the three of you. Please.
Yeah, I think in a similar boat. We will use whatever exists. We're excited for the capabilities in whatever way we can get access to them within our ecosystem. We will take part.
Clearly, yes, we're already doing it, but we're at day one. Like this is the very, very beginning of a very long journey, and there's a huge amount of opportunity for everyone in this room to be involved in some way.
Okay. Well, I think I might have not done as good of a job because there's no controversy here. So I think we have a problem here.